Welcome back. That's week 8 of our graduate statistics course, and we're continuing on with our exploration of what we can do with t-tests. So here's the question we're exploring right now. What is the difference in the amount of post-meal snack consumption between individuals that were distracted during lunch and those who were not? Here is our summary statistics. We always start there. And when we are running this in R, you see that the first step is to check those assumptions that we just talked about in the prior video. And to answer the question, what is the difference in the amount of post-snack consumption, we need to estimate a population parameter, here the mean difference, and a confidence interval. Would be nice to give us more confidence, or at least a desired level of confidence on that estimate. So as usual, for a confidence interval, it's always the same, a point estimate plus margin of error. Because we're asking what's the difference in the amount of post-meal snack, the point estimate would be the average difference, the difference between the two groups. And then we need to compute a margin of error of the t-distribution. I want you to hear me out, but without the tension that I have to memorize these formulas, because we're going to have a code for that. Right? A very simple, compact code to run t-tests. But I want you to work through this because I think it's important for you to understand it conceptually. So just like before, instead of having just one average, we're going to have two because we want the difference between them. We're going to have our t-critical that will create the margins to give us the level of confidence that we want. And we'll have the standard error of the difference that we need to compute. There's a little formula to compute that. It's a bit more complicated. The standard error of the difference is basically the weighed sum of the variance in one group, like the average, the weighed variance in one group, because it's the variance divided by, the variance in group 1 divided by the n, the sample size in group 1, plus the average, the variance in group 2 divided by the sample size in group 2. So you're kind of weighing, I'm kind of summing the variance of the two groups, but I want to weigh them by sample size, and I take the square root of that. So that's the standard deviation of standard error of the difference between means. Now, degrees of freedom for the t-distribution will be the smallest of these two. If I have in one group, let's say 21 people, and in the other group I have 20, the smallest one would be 20 minus 1, which would be 19, right? So in this case, the groups are the same size. So for both groups, n minus 1 is 21, so the two are the same. So I'll have to use 21, but if the two groups have unequal sizes, you're going to use the smallest value, because that will be the most conservative thing to do, which would give us the thicker tails. All right, so again, 95% confidence interval, you're going to have to get these boundaries for the t-critical, which is 2.08, which we've just seen. And then with that, we can apply the formula right there. We have the difference here, the t-critical here, and then we're applying the formula right there. So we have 40, this should be 45.1 squared, because it's this value squared, 26.4 squared, both divided by 22, and square root of that. And that gives the confidence interval that the difference in the amount of snacking is somewhere between 1.83 and 48.17 grams. So it's, we're confident that there is a difference there, but it could be very tiny or very large. So it's not a very precise confidence interval, which can happen when we have very small sample sizes, as we discussed last class. So all we know with this particular study, with this tiny sample size, is that there is, 0 is not inside of here, so 0 difference is not likely to happen. It's not a typical, it's not expected to be the mean difference, which means that we have a sort of a statistically reliable difference in the snacking patterns of individuals who are and are not distracted during lunch. But the magnitude of that difference is still pretty unknown. It could be small or large. So how meaningful that is different, right? But anyways, to answer this question first, I'm jumping ahead to hypothesis testing. Let's answer this question first. What is the difference in the amount of post-snack consumption? The difference is somewhere between 1.83 and 48.17 with 95% confidence. It's not a very satisfying answer again because it's not a very precise estimate. Future studies would have to increase the sample size to get a more precise estimation of that difference. So we're 95% confident that this difference is between 1.83 and 48.17. Now, question 2. Is this difference statistically reliable, meaning is this difference large enough for me to dismiss the null hypothesis that the difference is 0? There is no difference between a group that is distracted and a group that's not distracted during lunch. So to answer this question, we need a basis for comparison. Here, the comparison is between individuals that were and were not distracted, better than comparing to the recommended sample size, right? Recommended snacking portion, because this could or could not be equal to or similar to what the population at large consumes when they're not distracted. Now, do the data that we have provide convincing evidence of a difference between average post-meal snack consumption between those who eat with and without distraction? Do we have enough evidence? We can use, again, a quick and dirty assessment of this hypothesis by looking at the confidence interval. Because 0 difference is not here, we tend to think that finding the difference that we found is not likely under the null hypothesis. So we will reject the null hypothesis, considering a two-sided test that will divide the probability on the two tails, the rejection area in two tails. The 95% confidence interval would suggest that we would reject the null. Now, how would we get that probability of observing the average difference that we did observe? We have two groups. We have an average that's estimated from each group. And we have a null hypothesis that the difference is 0, and an alternative hypothesis that the difference will be different from 0. We have what we need to get our test statistic. So here is our standard error that we'll need for the test statistic. So it's 11.14. And here's the two-sample t-test formula. We get the observed difference minus the null, which is 0. And we divide by this value of standard error here. So 25 is the difference between these two, minus 0, which is the null. And here is the standard error. And we get a t-value of 2.24. If you're wondering where this number came from a mistake. This should be this number, okay? Now the degrees of freedom is 21 because the two groups have 22. So 22 minus 1 is 21. And here's our values of negative 2.24 and negative 2.24 and 2.24. We need both because we want the probability of getting something more extreme than absolute value of 2.24. So less than negative 2.24 or greater than 2.24. And we can use, let me put this down here. We can use a code in R to get that, right? So we get the absolute value of t, and we say that the lower tail is false. We want to get this probability, and we multiply it by 2, and we get the two-tail p-value, which is 0.03. So we reject the null hypothesis that there is no difference, right? And we stay with the alternative hypothesis. So note that the 95% confidence interval agrees with the p-value. So the p-value, would round up to 0.04. So we would reject the null hypothesis. The 0 is not contained within the interval, so it's not likely to get this interval here under the null hypothesis. And the probability of finding the average difference of 25 is pretty low, less than 0.05. We'll come back in a little bit. Sorry about the camera. Sometimes it goes bad. I'll stop and restart, but we'll come back with a different example in order to explore the last type of t-test that is available. So we explored the one sample t-test. That's when we had only one random sample, and we wanted to compare the observed mean to the expected mean under the null. We now just went through an example where we have two independent groups, and we wanted to know if the average difference between groups was equal to 0, which is the null hypothesis, or different from 0. And we use the t-test to examine these hypotheses. And now we're going to deal with a third situation where we have two means again to compare, but these means are produced in a paired way, in a non-independent way. So it's difference between two dependent population means. When we come back, I'll explore in more detail what that means. All right, see you soon. Bye-bye.